Hey guys, it's Greg. Today I am very excited to show you how to use PyCaret, probably Python's most popular automated machine learning library. I am truly fascinated by this thing's power and simplicity. It is so easy to use and it does an amazing job at visualization, finding the best machine learning model with absolutely no work at all. It's really cool and you really don't need to know that much about machine learning to use this. Just watch the tutorial. I hope you enjoy it, and let's get started. So I am using Google Colab. You can use your own environment, but it's easiest if you use Colab. !pip install -- pre PyCaret is going to get you set up with that library. It is going to take a while because it downloads a million things, and I'll see you at that point. Okay, at the end of all of this, you should see a warning to restart the runtime. So that's pretty easy. We just go to runtime, restart runtime, and we don't actually have to run that pip install again. We can forget that exists, and we should be good to go. Now, PyCaret closely interfaces with pandas, so we'll keep our datasets in pandas data frames. The most simple one that we can get after an import pandas as PD is df is equal to pd.read CSV, and just grab the classic California housing train.csv, which is stored in the sample data folder of Google Colab here. So if you are in your own environment, then I would recommend downloading that to follow along, or using your own data set, because it's very easy to kind of just use your own thing instead of what I'm doing exactly. Okay, so just to show you what df is and a brief summary, we have 17,000 rows and many different columns. Each row is an area in California, and they are all various continuous variables that describe an area in California. Now, usually this dataset is used to predict the median house value, and so we will just go ahead and run a regression, an automated regression with PyCaret to try and predict that column. So if we do from PyCaret.regression import star, I know it's kind of weird to see import star, that is actually what the docs use. S is equal to setup. We set up the dataset with, well, we pass it df, that's the data set that we want. And then we need to specify the column. Yes, column. It doesn't support multiple columns for regression right now. We do target is equal to median house value, which basically says that this is the column that we are trying to predict, or this is the column that we're trying to predict here. Since we're doing regression, it's trying to predict a continuous value. If this was a discrete set of classes, then it wouldn't make sense to do regression. We would do classification instead, and it uses all of the other variables by default as inputs to try and support that. So to zoom out a little bit so you can try and see multiple, I'm not going to show everything here because there's a lot, but basically there's a session ID, not important. It shows the target is what we said it was, and the type of it, we're doing a regression problem. Now our data shape is 17,000 by 9. You should recognize that from NumPy shapes. Why is it 9? Well, actually this whole data set is 9, and so it's not talking about just the input. It's talking about the whole data set, including the target column. Notice what it does here. It says train and test, even though we only had one data set. In fact, we loaded from what we call the train set, but really nothing knows that. And so we have one data set, and it automatically split this into train and test. So here you call this, we'd call this a holdout data set, because really just forget that you have it for now. Basically, know now that we have a data set with about 12,000 rows and 9 columns. Now, numeric features, we have 8 of those, and you might not be able to see this with the weird coloring, but preprocess says true. Imputation type is simple, so it does some simple, basically it has this set of rules that it follows to do some preprocessing, imputation, and other things. You can check the docs on what exactly it does, but basically if you were to do, if you wanted to normalize the data, it actually doesn't do that by default. If you wanted to normalize the data, you would have to do normalize is equal to true, and feel free to try it both with that and without that and see what's better. For now, we're not going to use it though. Okay, imputation, it does perform simple imputation and mean and constant imputation for numerical variables and categorical variables. Essentially, this means that it's going to replace the any missing values that are continuous with the mean of that column, and any categorical variables that are missing, it will replace it not with the mode, although you can tell it to do that. It'll replace that missing value with just this new constant that's like, this is missing. And feel free to check the docs on what exactly it's doing. I don't really want to make this the focus. I just want to tell you what is most important. Okay, notice that use GPU is false. I believe if you set runtime to a GPU type, it would use it. Feel free to check that out if you want, but I've had no problem so far with using this. What's really, really cool, which I'm not going to show in this video, but it does even allow for even just the slightest amount more of code. It allows you to use Spark and actually the whole clusters on Spark, which is really, really cool. So if you were working in a company, you had that kind of Azure cluster or whatever, you could easily set up PyCaret to work on there. Okay, but we're not going to do that. We are just going to look and try and find the best model. And we do that with the most simple code you could possibly think of. Best model, so best is equal to compare underscore models bracket bracket. That's it. And since we did that import as star, then it kind of knows that this is regression, and since we already called setup, it knows this data set. So I know this looks a little bit weird because we're not passing the data frame or anything like that. It just knows that since we called setup, that it is automatically comparing various models on that setup according to the different things that we passed setup, and we didn't really pass it anything interesting. There's a lot of other things, including normalizing like we talked about, that you could do in specific. But as you can see here, it's doing, so fitting tenfold, it's doing a tenfold cross-validation. And if you don't know what that means, don't worry. It's fitting many different models in a way that it can test it robustly. And it has all these different models that has the name that it refers to within PyCaret. It has a description of what it actually is. So lasso, least angle regression, something I don't even know what is. Linear regression, lasso, ridge, Bayesian ridge, some of the more common models. And then you'll see stuff like k-neighbors you'll probably recognize. I'm surprised we're not seeing any sort of tree-based models other than just a decision tree regressor, which is probably not going to do so well. But for all of these different models, we have basically the average, and so it has to be an average because we're doing a tenfold cross-validation. The average, mean absolute error, mean squared error, root mean squared error, and some other ones. These type of things, you want them to be low because they are errors. R2, you'd want that to be high. You can see it's kind of trying to get to 1, and so it highlights everything that it thinks is best. Here, almost all of it is best from this light gradient boosting model that it found, and then it seemed to have found the mean absolute percentage error was actually minimized by the random forest regressor. But we don't really care about that. Clearly, this model is the best. It got an RMSE of 48,636. Okay, so that's pretty awesome. Found the best model. What do we do? Well, we can look at a little more in specific what that model is with print best, since we stored that best model in that. And that seems to be all it's telling us. It actually told me a lot more about the model I made previously. I'll just show you the output it gave me when I did this earlier, and I don't think I did anything different. It actually gave me this with all of the specifics for this, still the same model, LGBM, but I don't know, apparently it's not telling us very much this time. Regardless, it found the best model, and now what we want to do is what we call finalize model with best. And now what that does is basically it trains it one more time, because all this did was find the best possible model through a cross-validation. Except how do you actually train a model? Well, you would do that through actually fitting it on the whole data set again. So given that whole original data set, yes, it's already seen it before, but that's okay. We give that whole data set to the model, this particular model that we're using, and that's what finalize model does. And it also tells you exactly what it's doing. That helps a lot more than this best does. This is the whole pipeline showing you the various things, what things it's including. So it chose to include 1, 2, 3, 4, 5, 6, 7, 8 inputs, which is actually everything, a simple imputer, and all this other stuff. And then there's the actual estimator, which is the regressor right there. Now the coolest part is evaluate model with best. And it's so cool. which it shows you all of these different graphs. It shows you this pipeline. It shows you different hyperparameters that it has. So this is a much better way. This is what print best should have done. But this shows you all the different parameters for this type of model. It shows you a plot against the residuals, which is very common for a regression type model. And that it actually shows you the R squared on that. And then there you go. So many other things. The one I really want to show you is that it also has a feature importance, which is there's kind of well-known things you can do with tree-based models for this. It thinks that longitude and latitude are most important, with the other ones kind of slowly going away. Note that I didn't normalize the data. You might see different results here if you did normalize the data. I encourage you to practice and do that yourself if you'd like to test it out. Okay, so a lot of different graphs here. I don't really want to show you everything. I'm going to move on to prediction. So firstly, you can just write predict model with best. Now, if you remember, we had that holdout set or test set from before, and note here that it's showing 11,899 until the end. So basically, it's showing a test data set, and this is the results on that test or holdout data set. All of the training and even that finalized model before, none of that was using that holdout set. That was all being trained on just that first partition. It first split it into train and test. Here's the results on that test data frame that the model has not seen, or none of the models, none of the process has seen this data set at all, which is a fair way of actually evaluating the model. So we can see here that this is our model, and these are results for the model. Very, very good. And again, you could go and normalize the data. Maybe it would be different. If you want you have another data set and you want to know how to predict on that, because given usually you make a model and then you actually want to use it later. But what you would do is have that in memory and you do test df. So we're going to get some new set of data. And unsurprisingly, it will be the sample data / California housing test.csv. And we can just see that test df is that same data frame there. It has all of the same columns. Since it matches perfectly, then it's okay. You would need it to have kind of the same column names. Otherwise, the model's going to be very confused. So we have a separate data frame for testing, and we do predict model with best and test df. So here we're actually specifying exactly that, hey, we don't just want to do it on our own holdout set. I have our own data set to pass here. And we are going to run that, and it will look exactly the same, except for this data set, which has 3,000 rows instead. And again, still very good results. So that's pretty awesome. That's for regression. And the only other thing you might want to do is save the model and move it elsewhere. I encourage you to do that on your own. And I leave that as an annoying exercise to the watcher, I guess. That's like that annoying thing you say in a book, like I'll leave it as an exercise to the reader. That is exactly what I'm doing. Now on to classification. And it's going to look extremely, extremely similar because it's equally as high level, but things will visually look a little bit different. So I'm going to use the Titanic dataset, and I'm going to have assumed that if you're following along, that you've clicked the link in the description of the video, and then you've downloaded train and test.csv, and then uploaded them back into Colab if that's what you're using. That's what I'm going to do off screen right now. Okay, so magically I have train and test.csv. Again, that link's in the description if you're looking for it. And here we go. So we're going to load up our data frames because that's what it uses. Titanic Train is equal to pd.read csv train.csv. And I'm going to load in test at the same time. Titanic _ test is equal to pd.read csv with test.csv. And then I will just show you Titanic Train. Now for this one, there is a very slight difference between train and test, because if I show you Titanic test, well, that actually has 11 columns, and that's because it's a Kaggle problem. And usually what it's doing is predicting this one that will be missing for the test, which is the survived column right here. So normally this is a binary classification problem on this people on the Titanic. We have many different variables regarding each person on the Titanic, and normally you're trying to predict whether they survive or not. Now for us, I just want to make it a classification problem because it's a little bit more interesting than a binary classification problem. So we're going to do this and pretend we're trying to predict P class. which is essentially the class for a person. The higher class is basically denoted by 1. So it's 1 is the best class, and then 2 is the second best class, and then 3 is the third class. Basically, first is upper, second is middle, third is lower class. So you want to have a lower number. Now, before we get going here, I do actually have to drop this column. So we have to do Titanic _ train.drop survived. We have to drop the survived column because it's not going to show up in the test set. Survived axis equals 1, that says column, and in place equals true, just to go ahead and do it in that one line, and then it should be done. Okay, so before we get started, I do just want to show you a value counts for interest's sake. Titanic _ train sub p class, that's the category, that's the variable we're trying to predict here on a classification problem, dot value counts bracket. Okay, so we basically have 216 lower or upper class people, 184 middle class people, and 491 lower class people. So maybe the model might be a little bit better at predicting lower class people because there is more of them, but you know, we'll see what it does, and it's probably going to do pretty well. So what do we do now? Well, we did before from PyCaret.regression import star. We're actually going to overwrite those variable names and do from PyCaret.classification import star. Okay, and we'll do exactly the same thing, like literally the same thing. S is equal to setup with the dataset Titanic _ train, and target is equal to the P class, because that's what I decided for this we want to predict. And again, I don't believe it supports doing like multiple things at the same time. It has to be just like one column. And so we'll do a setup there. And let's take a look what it outputs. So it gives a session ID, not overly interesting. It says the target's the class. It's a multi-class classification problem, so it got that right. And here there's a bit of a mapping, and so it's doing an automatic mapping that's showing it for the P class right there. It's basically mapping 1 to 0, 2 to 1, 3 to 2. Don't really need to worry about that. And then the original data shape, transform data shape, it actually added 1. Okay, so categorical features is 5, numeric features is 5, ordinal features is 1. And rows with missing values is 79.5%. So even though it is missing a ton of values here, and there's really weird data, like you can see there's just names here, it hasn't complained at you, which is pretty awesome. Scikit-Learn most definitely would have yelled at you for many different reasons by now. But it's just kind of dealing with these problems as it sees them, doing an imputation. And it actually has to do it this time because, well, 79.5% of the rows have missing values, but it's not going to discard them. So again, for imputation, it will do it in a simple way. You could change this to iterative if you wanted and make it more complicated, but for now, it is going to do a mean imputation. Again, replaces the continuous value that is missing with the mean of that column, and a categorical imputation. If it's missing for a categorical variable, it replaces it with a variable, or basically just a class that says this is missing. Okay, so it shows some stuff about one-hot encoding, not too concerned, and it's going to do a k-fold cross-validation. Okay, so we'll go ahead and do exactly the same thing. Best is equal to compare models, and what's really just cool is that this doesn't break. And it's fascinating that this doesn't break because I purposely picked a weird data set that is, you know, there's problems all around. There's not a numbers in this categorical column, which is made up of these strings. There's these names, and somehow, some way, it just doesn't care. And so it's going to do whatever it can to ignore that, figure out what the best thing is to do, and it's going to try all these different models on that pre-processed data. So there you go. It got the best models. Almost everything is from this extra trees classifier, which has a high accuracy, AUC, recall, precision, F1, kappa, MCC. This is Matthew's correlation coefficient, which you may not have heard of, but is arguably the best number to try and maximize. And it's easily maximized by this extra trees classifier right here. And then this random forest classifier seems to have maximized the AUC, but we're not going to really concern ourselves with that. So let's see what happens when we print best this time, because it should actually show us more than it did before. There we go, extra trees classifier, and I guess this one's a little more complicated than the last one. Like before, we are going to finalize the model, and what does that do as a recap? Finalize model with best is going to, given that training set, note again, we have a training set and a test set. This is separate from that Titanic test dataset that we got. This is still all from the Titanic training dataset, but it split it into a training set and a test set. All of the training that's been done has been on this training set and actually a partitions of that to do cross-validation. But here we do finalize model. Basically just says, hey, give me this whole training set of data, train a model on that, train that particular model that we found was best. And we still at this point haven't seen the test data. Okay, so if we go down here, we should see that we finalized our model and that is fully trained. Now what can we do? Evaluate model on best. Evaluate model is gorgeous as always. We have the pipeline plot, which shows the raw data, goes into various encoders and imputers. Not going to worry about all the specifics there, but that shows you the different pipeline things that it does. Hyperparameters shows you in particular what this model has for, so 100 estimators or 100 trees and various different things. Not going to worry about it. AUC, which is the ROC plot. It's going to show that for each of the different classes. So pretending each of the classes are kind of the positive class and the others are the negative class. It's going to have an AUC for all of those. And they're all individually very good. Hence the micro and macro average is extremely high as well. Of course, you can get a confusion matrix, which is probably the most common plot for any classification problem. Shows you where it got it right and where it got it wrong. So apparently when it predicts 2 and the true class is 1, that's actually when it's getting it wrong most. I'm not really going to try and calibrate that, although that's kind of important to know that that is the most common error that it has. And so many other plots. I'm just going to show you feature importance is a good one. It shows that cabin is the most important variable by far, and then ticket and fare are next important, and then these other ones are kind of less important. Okay, so truly wonderful graphs there. We can then do as before, we can do a predict underscore model with best. What does that do? That predicts on that test set and reports the same metrics as before. And so on this data set, on this holdout data set with the model, we have this accuracy, AUC, all of that stuff holds up on the test data set, proving that this thing is robust since it hasn't seen that test data set before. And then if you really wanted, again, this is just another, basically a second layer of testing if it's still working. It's just another holdout set really. Predict underscore model with best and Titanic test. That's how we separated it at the beginning. And it's just the data set that we were given. Predict model best on Titanic test should be extremely similar. Actually, it seems to be even better. 9.455 Matthews correlation coefficient compared to, well, a lot less. Okay, so apparently that data set was even better. I'm not quite sure why. That's how to use PyCaret for regression and classification. It does some other stuff as well. I am very likely to in the future show you how to do some other things because I'm excited to do some more with it as well. Drop a like on the video if you found this helpful. I think it's really cool. Let me know your thoughts on this library down below. I think it's awesome. And yeah, I'll see you later, guys. Have a great day.